So if you break your arm, right? There's a certain comfort in the X-ray. You hold it up to the light and you see that jagged white line, and the doctor just points at it, and it's like, okay, it is broken. The problem is totally visible.
Right. Yeah, it's tangible.
Yeah, exactly. Even with older cars, if your suspension snaps, you hear a massive clunk. The physical world gives you very clear evidence of a failure. But modern electric vehicles, I mean, they are completely different beasts.
Oh, yeah, absolutely.
We tend to think of them as just cars with giant batteries, but really they are high-speed rolling computer networks.
Which completely changes the nature of a breakdown.
Yeah.
When you're traveling at, say, 70 miles per hour down a busy interstate, your vehicle isn't just mechanically turning a drive shaft anymore.
Right.
It's processing millions of lines of code. It is sending constant, microsecond level updates between dozens of different computer brains.
Okay, let's unpack this, because this is where the mystery really starts for me. Our mission for this deep dive is to explore a highly critical engineering document we got our hands on. It's a deep-level technical specification dealing with something engineers call CAN message loss, or timeout in electric vehicles.
Right.
And we are not talking about your infotainment screen freezing so you can't change the radio station.
No, this is much more serious.
Yeah, we are looking at a safety scenario classified as ASIL D. That is the highest possible automotive safety integrity level. It deals directly with the core propulsion system.
Yeah, so to understand the stakes here, you have to imagine you are merging onto that interstate. You press the accelerator pedal.
Yeah.
In an older car, you pull a physical cable that opens a throttle valve.
Just simple mechanics.
Right.
Yeah.
But in a modern EV pressing, that pedal just generates a digital request.
Okay.
It tells the vehicle control unit, which is the central brain of the car that you want to accelerate. That central brain then has to send a digital packet of information across a network cable to the dual motor controller.
Just to tell the electric motors to spin faster.
Exactly. It's a network message.
So what happens if that message just drops? What if that tiny packet of data vanishes into thin air while I literally have my foot to the floor?
Well, that is exactly the terrifying scenario this document addresses. Because if that communication drops, the car is suddenly flying completely blind.
Oh, wow.
The central brain doesn't know what the motor is doing, and the motor doesn't know what the driver wants. So in engineering terms, this triggers what is called the fault-tolerant time interval, or FTTI.
FTTI, meaning the clock starts ticking the absolute millisecond a message goes missing.
Yes, and it is a microscopic window of time. The system has to realize a message is gone, figure out why it's gone, and safely reduce the power of the motors before you experience a catastrophic loss of vehicle stability.
And we're talking about preventing the car from violently locking its wheels at highway speeds, right?
Right, or getting stuck accelerating uncontrollably. And this all has to happen in under 1/10 of a second.
Under 1/10 of a second. It's basically a completely invisible war happening under the floorboards.
Yeah.
So before we look at how the car actually saves itself from the armor, so to speak, we need to understand the invisible forces that are actively trying to destroy that data packet in the first place. Because from what I'm reading, the environment inside an EV is incredibly hostile to delicate electronics.
Oh, it is incredibly hostile.
Yeah.
The engineering spec details 4 distinct root causes for these communication failures.
Yeah.
And the first one is essentially electromagnetic warfare happening inside the chassis.
Yeah, the document refers to it as high DVDT and ADE EMI coupling.
Right.
Which honestly sounds like absolute alphabet soup to me, so let's translate that. Modern EVs use silicon carbide or SiST transistors for power modulation, right?
Yes.
They are basically massive electronic switches that turn the high voltage battery power on and off to physically spin the motor.
And they switch at speeds that are honestly almost difficult to comprehend. The specification notes voltage changes of greater than 10 kilovolts per microsecond. In extreme cases, they swing 50 volts per nanosecond.
Okay, let's try to ground that for a second. Imagine you are trying to have a very delicate, whispered conversation with a friend across a room.
Okay.
That whisper is the communication signal on the car's network, the CAN bus. It operates on tiny voltage differences, just a couple of volts to send ones and zeros.
Right.
Now imagine someone sets up a heavy machine gun right next to your ear and just starts firing.
Yeah.
The machine gun is the electrical switching of those silicon carbide motors.
That's a great analogy. That switching creates massive electrical interference, specifically common mode noise. Now, theoretically, the cables carrying your delicate whisper are shielded.
Like physical armor.
Yeah, they have a metal braid around them to block that noise. But the physical reality of a car is messy. Over years of driving, that shielding can degrade slightly. A ground connection might get a tiny bit loose.
And so when that armor slips, the machine gun noise bleeds right into the delicate conversation.
Exactly. It physically alters the voltage on the communication wires. The CAN bus works by looking at the difference in voltage between two wires to determine if a bit is a 1 or a 0.
Right, what they call dominant and recessive levels.
Right. And when that massive electromagnetic spike hits, it scrambles those voltage levels. A 1 suddenly looks like a 0. The data packet just gets completely corrupted.
And the communication chips actually, no, this is happening, right? The spec mentions they have internal error counters.
They do, yeah. Every time a message fails, this cyclic redundancy check, which is basically a mathematical seal of approval on the data, the counter ticks up.
Oh, I see.
And it counts up rapidly. If that interference is sustained and the error counter hits 255, the chip is programmed to essentially give up.
Give up.
It enters a bus-off state. It physically disconnects itself from the network to protect the rest of the system from its own corrupted garbage data.
Which means the brain just intentionally severed its connection to the motor because the noise was too loud. That is terrifying. But okay, noise is just one way to break the signal.
Yeah.
What about the physical wires themselves? Because you have solid metal pins plugged into solid metal sockets. Surely those don't just randomly disconnect, right?
Well, you would assume a plugged-in wire stays plugged in.
Yeah.
But the second major threat the document outlines is mechanical. It is something called pin fretting corrosion.
Pin fretting. Now, this one blew my mind because of the scale we're talking about. The control boxes are bolted to a car that is constantly vibrating. The motor itself creates high-frequency vibrations anywhere from like 100 to 1,000 hertz. Plus, the temperature is swinging wildly depending on the weather and the heat of the battery, going from -40 to positive 125 degrees Celsius.
Yeah, and that combination right there of thermal expansion and high-frequency vibration, it causes the metal connector pins to slide back and forth against each other.
Okay.
But we are not talking about visible movement. We are talking about 10 to 100 microns of movement.
Wait, I have to stop you there. A micron is a millionth of a meter. A human hair is like, what, 70 microns thick?
Roughly, yeah.
How does a movement smaller than the width of a hair actually break a solid electrical connection?
Because, well, at a microscopic level, solid metal isn't perfectly smooth. It looks like a jagged mountain range.
Ah, okay.
When those two jagged surfaces slide against each other at high frequencies, which engineers call fretting, it acts like ultrafine sandpaper.
Oh, geez.
It physically scrapes off the conductive surface coating on the pin, like the tin or the light gold plating.
So it is literally wearing the metal away just by vibrating.
Yeah, and it gets worse.
Yeah.
By scraping the plating away, it exposes the underlying base metal to oxygen.
Right, and oxygen causes rust.
Exactly. It creates a microscopic layer of oxidation, basically rust. Now, oxidation is an insulator, so suddenly the electrical resistance between those two metal pins just skyrockets.
So the wire is still physically plugged in. It looks totally fine to the naked eye, but the data is hitting a microscopic brick wall of rust.
Yes. And at the exact peak of a severe vibration, that oxidized layer causes microsecond or sometimes millisecond physical disconnections.
Wow.
And in a computer network that is waiting for a critical torque command every few milliseconds, that microscopic disconnect is enough to trigger a total communication timeout.
That is just unbelievable. Okay, so we have electromagnetic noise blasting the signal, and we have microscopic earthquakes rusting the pins. The third threat doesn't even exist in the physical world.
No, it's pure software.
Right, it's purely a software issue. The spec calls it task priority inversion.
Yeah, this is a fascinating problem of resource management within the microchip itself. Because the motor's core operating algorithm, which calculates exactly how to spin the magnets, it runs in a very tight loop.
Usually every 100 microseconds,
Yeah.
right?
And it operates at the highest priority interrupt level, meaning it gets to demand the processor's attention whenever it wants.
While the town communications stack the software that actually receives and unpacks the network messages that runs in the background on a much slower 10 millisecond loop.
It's a classic bottleneck.
Yeah, it makes me think of a VIP at a crowded high-end restaurant. The VIP is the motor algorithm, and they are completely hogging the waitstaff. They are demanding constant service, ordering new drinks every 10 seconds.
Right.
Meanwhile, the communication data is just a regular customer standing out in the cold rain waiting for someone to open the door and take their coat.
That analogy perfectly captures the mechanism. Let's say the vehicle suddenly faces a burst of heavy mathematics.
Okay, like what?
Maybe you just drove through a puddle, right? The wheels slipped, and the traction control system suddenly needs to calculate a complex thermal resistance model on the fly.
Oh, so the processor has to do a ton of math all at once.
Exactly. That high-priority motor algorithm suddenly consumes 100% of the processing power.
Meaning the wait staff is completely overwhelmed.
Yeah. And if the operating system lacks strict protocols to prevent what we call priority inversion, that background communication task just gets infinitely delayed.
So wait, the data packet physically survived the electromagnetic noise. It made it past the microscopic rust on the pins that actually arrived at the chip.
The data is sitting perfectly intact in the CAN buffer on the silicon, but the processor is simply too busy to read it.
Oh, man.
To the vehicle controller, it looks identical to a severed wire. It triggers a communication timeout, a fake software failure, entirely because the processor was distracted.
Wow. Just a fake failure. Okay, the fourth and final root cause in this section of the spec is low voltage power sag.
This goes back to the reality of the car's physical environment. Everything we've discussed relies on a very stable power supply.
Right.
But when you stomp on the accelerator, or even when the air conditioning compressor kicks on hard, it puts a massive transient load on the entire electrical system.
The document notes that a standard 12-volt battery system in a car can temporarily drop down to 6 volts for about 20 milliseconds during a heavy load.
Yeah, and for a traditional light bulb, a 20 millisecond drop to 6 volts just means the headlight dims slightly, so fast you might not even notice.
But to a delicate computer network, it's a massive brownout.
Exactly, because that 12-volt supply feeds the 5-volt power rail on the communication circuit board.
Yeah.
When the 12-volt supply sags, the 5-volt rail literally shakes.
And remember how we said the CN bus communicates by looking at voltage differences? It requires that differential voltage to stay above 1.5 volts to successfully register as a valid signal.
Right, so if the main power sags, that 1.5-volt gap shrinks.
The signal just loses its definition.
Yeah, the receiving chip looks at the wire and just sees a blurry mess. It can't distinguish a 1 from a 0, and the message fails to unpack.
Man. So we have a communication network operating in what is essentially a localized hurricane.
Pretty much.
It's being blasted by electromagnetic machine guns, shaken to death by fretting corrosion, ignored by its own distracted CPU, and periodically starved of power by voltage sags.
Yes, it's
What?
a miracle it works at all.
Which brings us to the most critical question of this entire deep dive. How on earth does the car survive this? Like, if dropping a single message at highway speeds can cause the motors to lock up, how do engineers build a digital immune system to handle this chaos?
Well, this is where we move from the vulnerabilities to the actual architecture. We have to look at how an ASIL D system detects one of these failures within that microscopic 100 millisecond fault-tolerant time interval.
Right, the FTTI.
Yeah, and how it reacts without causing a crash.
Let's start with the first layer of defense, which from the spec is basically a policy of trust, but verify. The engineering spec calls it AutoSAR E2E, or end-to-end data integrity verification.
Yes.
Any message that holds that critical ASIL D safety rating, like the target torque command from the driver's foot, is wrapped in this digital armor.
It utilizes AutoSAR E2E Profile 1, adding several mandatory, non-negotiable checks to every single packet of data before it is allowed to be processed.
Let's list the armor here because I think it's brilliant. First, they use CRC8 checksums.
Right, the mathematical check.
Yeah, the sending computer runs complex polynomial math on the raw data bits, generates a unique number, and attaches it to the message.
And then the receiving computer runs the exact same math.
Right, and if the numbers don't match, it knows a bit was flipped by interference, and it literally throws the message in the trash.
Exactly. Second, they use data IDs. This ensures messages don't get confused or accidentally cross-wired in the software routing, The torque command always identifies itself specifically as the torque command.
But my absolute favorite piece of this armor is the alive counter.
Oh, yeah, that's a good one.
It is such a simple, elegant solution. It's literally just a number from 0 to 15 attached to the message, and it counts up with every single frame sent.
Frame 1 is 1, frame 2 is 2.
Exactly.
It is elegant because it completely solves the problem of a frozen system. If the central brain locks up and just starts broadcasting the exact same message over and over.
Like, say it freezes on the command for 100% throttle.
Right. The receiving motor controller doesn't just blindly obey. It actively looks at the alive counter.
So if it sees that counter freeze at, say, 7 for 3 consecutive frames, it instantly knows the sender is brain dead.
It doesn't wait to find out why. It immediately flags a failure and stops listening.
That is so smart. And that leads to the second layer of architectural defense, which the spec calls the hardware mirror or the loopback check.
Yes, this is where the physical transceiver chip, the tiny component that actually pushes the voltage out onto the wires, becomes its own diagnostician.
Okay, let me see if I grasp this properly. The chip has a transmit pin and a receive pin. You're saying it actively reads its own physical signal as it's sending it out?
It is constantly comparing its outgoing channel, the TX, to its incoming channel, the RX. So imagine you are shouting down a hallway, but you are also wearing a microphone that feeds your own voice back into your earpiece.
Okay, so if I try to shout but I hear absolute silence in my earpiece, I know my vocal cords are broken.
Exactly the same principle. If the transceiver tries to push a high voltage out onto the CAN bus, but its own receive pin reads a low voltage, it knows instantly without a shadow of a doubt that there is a physical short to ground or an open circuit on the physical wire.
Wow. And according to the spec, it throws a DTC U0100 fault code right then and there.
Instantly.
It catches the broken wire internally before the main computer even has time to realize it's missing a message from the network. It self-diagnoses at the speed of light.
But what happens if the main processor itself, the core calculating the motor speed, locks up?
Oh, right.
That brings us to Layer 3 temporal monitoring via a dual checker architecture.
Now, this part is wild to me. You essentially have a dual-core setup in the car. It's like having two pilots sitting in the cockpit of a commercial airliner.
That's exactly it.
The main core, the doer, is actually flying the plane. It's reading the pedals, updating the torque, managing the inverters. But the safety core, the checker, it doesn't fly the plane at all.
No, the checker just sits there with a stopwatch.
A stopwatch.
In industry terms, it is an independent watchdog timer. This is the ultimate failsafe against that priority inversion software ghost we talked about earlier.
So why do you need two completely separate cores for this? Couldn't you just program the main core to check itself?
Because if the main core goes insane, it can't be trusted to diagnose its own insanity. You know you need a completely independent observer.
Right, that makes sense.
The checker strictly monitors a 50 millisecond timestamp. If the doer goes quiet, if it fails to process a new valid instruction within that 50 millisecond window, the checker violently takes over.
It literally physically interrupts the main processor.
It forces a hardware reset or overrides the control pins. Imagine that merging scenario again. You press the accelerator to pass a truck. At that exact moment, a single stray cosmic ray or a boost of EMI flips a critical bit in the processor's memory, causing the software loop to hang.
And without the checker, the car would just keep accelerating infinitely because it froze on the full power command.
Exactly. But the checker sees that 50 millisecond delay, a door is dead, and overrides the entire propulsion system to protect the driver.
Which triggers layer 4, the soft landing or the ramp down to safety. Because I gotta tell you, this was my biggest misconception going into this document.
Oh, yeah.
I initially thought, hey, communication lost, the computer's frozen, just cut the power to the motor immediately, turn it off.
Well, that is the natural human instinct. Engineers call it safe torque off or STO.
Yeah.
Just sever the power entirely.
Yeah.
But in an electric vehicle, abruptly cutting power to a high-mass magnetic rotor that's spinning at thousands of RPMs is incredibly dangerous.
The physics of that are brutal. The document states that an abrupt electrical shutoff would cause a massive back EMF spike, which creates extreme mechanical resistance.
It could violently lock the wheels.
Yeah, it said it could lock the wheels. So if you were going 70 miles per hour and your rear wheels suddenly lock up, you were going to spin out and crash. Or, at best, you decelerate so rapidly that the semi-truck behind you just rear ends you.
This is where the precise math of safety comes in. The car doesn't just cut power. Once that 50 millisecond timeout is confirmed, the system initiates a highly controlled ramp down.
It smoothly reduces the power output.
Yes, at a mathematically calculated rate of exactly 1,000 newton meters per second, aiming for zero torque.
It bleeds the kinetic energy out of the system rapidly but smoothly enough to preserve vehicle dynamics.
Exactly. It won't upset the suspension or break the traction of the tires.
So once the torque is safely under 5 newton meters, or after exactly 50 milliseconds of ramping down, the system finally locks, the power triggers the PWM signals and enters what's called AOC, active open circuit.
AOC essentially puts the electric motor into a safe freewheeling state.
Yeah.
It allows the wheels to spin freely without generating or consuming power.
So the car's ultimate safety protocol when its own internal network is completely collapsing is to prioritize gravity and physical momentum over a raw electrical shutoff. It uses sophisticated software to manage a 2-ton piece of metal, gracefully forcing a safe coasting scenario so the driver can just pull over.
It really is a remarkable safety net. But as any engineer will tell you, diagnostics and fail-safes are really just for catching errors after they happen.
Right.
The true art of engineering is designing the hardware so these ghosts never get into the machine in the first place.
Which brings us to the actual physical blueprints. The design failure mode and effects analysis, the DFMEA.
Yeah.
How do they bulletproof the board physically?
So we move from software back into hard physics here. Step 1 in the DFMEA is isolation, building a wall.
The spec details how CAN FD transceivers use automotive-grade digital isolation chips, and they boast a common mode transient immunity, a CMTI of greater than 100 kilovolts per microsecond.
Which directly combats that first ghost, the massive EMI noise from the power switching.
Right, but looking at the physical circuit board design in the document, it goes much deeper than just picking a good chip.
Oh, definitely. The trace routing on the circuit board itself is meticulously controlled. They require strict 120 ohm impedance matching on the copper pathways.
And they place these tiny, highly specific components called common mode chokes right at the connector pins.
Yes.
Now, the spec requires chokes with over 2,000 ohms of high-frequency impedance and 51 to 100 microhenries of inductance. I need you to explain this to me because to a layman, adding impedance sounds like you're intentionally making the signal weaker.
Right. I can see why you'd think that.
How does a choke actually work?
So think of a common mode choke as a physical bouncer at the door of a nightclub.
Okay.
The choke is essentially 2 coils of wire wrapped around a magnetic core. Now, normal communication data, the differential signal flows in opposite directions on the 2 wires.
Well, one goes positive, the other goes negative.
Exactly. And because they throw in opposite directions, their magnetic fields cancel each other out inside the choke. They pass right through, invisible to the bouncer.
Oh, that's cool.
Hmm.
But the noise, the electromagnetic interference from the motor, that's common mode noise. It hits both wires going in the same direction at the same time.
Precisely. And when that high-frequency noise hits both coils in the same direction, the magnetic fields don't cancel out, they add together.
Oh, wow.
This creates massive inductive resistance. The noise literally chokes itself off. The higher the frequency of the noise, the harder the bouncer pushes back, physically preventing that chaos from entering the delicate silicon chip.
That is an incredibly elegant use of basic physics. I love that. But what if the noise is so loud that some of it manages to slip past the bouncer?
Well, then they employ the second design feature, split termination, which acts as a noise drain.
Split termination. Okay. Traditionally, if you build a communication network, you put a single 120 ohm resistor at the end of the wire.
Right, it acts like a shock absorber, stopping the signal from bouncing off the end of the wire and echoing back down the line.
But in these ASIL D electric vehicle architectures, they don't use a single 120 ohm resistor. They split it into 2 separate 60 ohm resistors. And the spec mandates these aren't just standard resistors. They require 0.1% precision.
And here is the magic trick. They take the center point, the exact middle connection between those 2 60 ohm resistors, and they tie it to a very specific 4.7 nanofarad C0G ceramic capacitor, which then connects straight to the ground plane of the chassis.
Why go through all that trouble? Like, how does tapping the middle of a resistor filter anything?
Because it creates a trapdoor. Remember that the valid data signal is differential. It balances itself perfectly across the 2 wires, so the voltage exactly at the midpoint between those resistors is functionally 0.
Oh, so the data ignores the trapdoor?
Yes, the data doesn't even see it. But the common mode noise is a massive voltage spike hitting both wires simultaneously.
Right, so the noise hits those resistors, finds that center tap, and sees that ceramic capacitor.
And to a high-frequency RF noise spike,
Right.
a capacitor looks like a wide-open highway straight to ground. It gives that deadly interference a path of least resistance to drain safely away into the chassis, far away from the communication wires.
That's genius. So they use magnetic fields to choke the noise and a precise capacitor trap door to drain whatever is left. Step 3 in the design blueprint focuses on timing, synced clock source, and routing.
This goes back to those extreme temperature swings we talked about earlier,
Yeah.
going from freezing cold to boiling hot.
Yeah.
As the silicon inside a microchip heats up the crystal oscillator that provides its internal heartbeat, its clock can drift slightly.
The tick-tock gets slightly faster or slower.
Right. And if the sending chip and the receiving chip are relying on separate internal clocks and one chip gets hotter than the other, their timing drifts apart.
Oh, they stop understanding each other. The bit timing is ruined, and the ones and zeros get misaligned.
To prevent this, the spec forces both the main microcontroller unit and the external communication chips to share one highly stable external hardware clock.
So by physically tying them to the same master heartbeat, even if the temperature swings wildly, they drift together, remaining perfectly in sync.
Exactly. And the physical routing of the wires themselves is heavily regulated. High-density twisted pairs with greater than or equal to 33 twists per meter.
And they must be physically routed at least 150 millimeters away from the high-voltage CC bus. They literally keep the low-voltage whisper cable physically separated from the high-voltage machine gun.
The physical design must respect the laws of electromagnetism, you know. You cannot cheat the physics.
Which brings us to a harsh reality. A perfect blueprint full of chokes and trapdoors and synchronized watches means absolutely nothing if it is assembled wrong on a Tuesday morning at the factory.
Oh, absolutely.
This transitions us to the process failure mode and effects analysis, the PFMEA. How does a modern automotive factory ensure absolute perfection?
Well, when you are dealing with ASIL D safety requirements, manufacturing requires removing human variability entirely. You have to guarantee physical immobility at a microscopic level.
Let's look at the first process control X-ray vision on the assembly line.
Yes.
The spec outlines that factories use 100% 3D automated X-ray inspection, or 8XI. They literally take a 3D X-ray of the solder joints on these communication chips as they come down the line.
They are hunting for voiding.
What?
Yeah, when metal is melted to solder, a chip to a board, microscopic empty air pockets can get trapped inside the molten metal.
The tolerance here is insanely strict. I mean, total voiding in a joint must be less than or equal to 5%, and no single microscopic void can be larger than 1% of the joint's area. Why such a fanatic obsession over a tiny air bubble inside a piece of metal?
The reasoning goes right back to the thermal stress we discussed. Imagine a car operating in negative 40-degree weather, and then the circuit board heats up to 125 degrees. The metal solder and that trapped tiny pocket of air, they expand and contract at different rates.
So the bubble is literally fighting the metal from the inside out.
Over thousands of heating and cooling cycles, that differential expansion causes the solid solder to fatigue microcrack and eventually sever the can connection entirely.
Oh, wow. So a 2% bubble of air on a Tuesday becomes a total loss of motor control on the highway 3 years later.
Exactly.
So they X-ray every single board to find the bubbles. That is wild. Next process control, the smart wrench automated crimping. This directly combats the fretting corrosion, the microscopic sliding of the pins.
Right, to prevent that 10-micron sliding, the way the copper wire is crimped into the metal connector pin is tightly controlled. They mandate 360-degree high-precision crimping with closed-loop force displacement monitoring.
It is a robotic tool that physically measures the exact resistance of the copper wire as it crushes the metal pin around it. What happens if the wire they loaded into the machine is just a fraction of a millimeter too thin?
The robotic tool instantly knows the pressure curve is wrong.
It just feels it.
Yeah, it feels it. The crimp isn't perfect, and it doesn't just flag the part to be looked at later. The machine is integrated into the factory's software to instantly lock down the entire production line until an engineer investigates.
Because a loose crimp allows oxidation, which kills the signal.
Exactly.
And finally, before this controller ever gets put into a cardboard box and shipped out, it faces the final exam. End-of-line testing.
This isn't just a basic power-on test either. The testing rig actively attacks the CAN bus on the finished unit. It tests if the unit fails correctly.
The automated rig artificially injects physical shorts to ground on the wire. It deliberately drops frames. It blasts it with noise to force a bus-off fault.
And it verifies with 100% certainty that the unit recognizes the failure, throws that exact U0100 diagnostic code we talked about, and triggers that smooth 50-millisecond ramp down flawlessly.
And if it doesn't hit that 50-millisecond window perfectly on the test bench, it just goes straight in the trash.
It goes in the trash. It's a trial by fire on the assembly line.
Yeah.
But you know, even before mass production is ever approved to start, the fundamental design has to be proven.
Right.
Which brings us to the ultimate proving ground, the design verification plan and report, the DVPNR.
This is where the engineers take their prototype systems and subject them to the most brutal physical and digital torture tests imaginable. The first one in the spec is the electromagnetic hurricane. Limit EMI injection testing to ISO 142 standards.
Yeah, they put the complete system in a specialized chamber. They spin the motor up to 12,000 RPM at full load, so the silicon carbide switches are blasting at that 10 kilovolts per microsecond rate.
And then, as if the motor's own noise isn't enough, the engineers deliberately attack the wiring harnesses. They blast the cables with a 200 milliamp current injection and bombard the entire setup with 100 volts per meter of dynamic electromagnetic radiation.
And under that immense artificial level of interference, the acceptance criteria is absolute zero compromise. The isolated communication link must maintain a signal-to-noise ratio of greater than or equal to 48 decibels.
It's like whispering to your friend while standing next to a jet engine while someone else shines a spotlight in your eyes, and your friend still hears every single syllable perfectly.
There must be absolutely zero frame loss.
Test 2 is arguably even more brutal, the shake and bake. Vibration and thermal shock to ISO 16753 standards.
They mount the entire control unit on an industrial rig that physically shakes it on 3 axes simultaneously.
Random vibration with a force of greater than 35 meters per second squared.
While it's violently shaking, the environmental chamber rapidly swings the temperature from -40 to positive 125 degrees Celsius back and forth.
And they force the network to run at 80% data capacity through all of this for over 1,000 continuous hours. The sheer brutality of this is stunning. And what are they looking for when it's over?
Well, they measure the electrical resistance of those crimped connectors. Remember the fretting, corrosion?
Yeah, the rust.
The resistance cannot increase by more than 1.2 milliamps after 1,000 hours of shaking. Furthermore, during the entire ordeal, there can be 0 communication disconnects longer than exactly 1 microsecond.
If the signal blinks out for 2 microseconds while being shaken to death, the prototype fails.
It fails.
And the final torture test, the digital matrix, hardware in the loop, or HL fault injection.
They hook the physical engine controllers up to a massive supercomputer simulation.
Okay.
The computer simulates the physical car driving at highway speeds, the motor virtually spinning at 12,000 RPM.
And in the simulation, the engineers digitally sever the torque message from the central brain for exactly 50 milliseconds.
This is the ultimate proof of the entire safety architecture. This proves the FTTI response time actually works in the real world, not just on paper.
The system has to detect the digital severance immediately, and the motor must automatically initiate that ramp down of its torque at exactly 1,000 newton meters per second.
And the sensors measure the output, and it cannot have any torque jitters over 5 newton meters during the ramp down.
It must end securely in that active open circuit state.
Meaning 0 demagnetizing current and absolutely 0 wheel lock. The simulated vehicle must coast safely every single time without exception.
Okay, we've covered a massive amount of ground here. We started by exploring the invisible threats, the electromagnetic noise blasting the voltage, the microscopic earthquakes rusting the pins, and the priority traffic jams in the software processor.
We looked at the dual-core safety watchers acting as fail-safe pilots, ready to take over and softly land the car.
We examined the extreme physical armor from the magnetic bouncers of common mode chokes to the 3D X-ray inspections catching microscopic air bubbles in the factory.
All the way to the 12,000 RPM torture tests.
It just highlights how much invisible armor goes into keeping a driver safe every single time they press the pedal. It's truly a miracle of modern engineering.
It is a monumental achievement. But looking at the very end of the source document, provided there is a highly specific detail regarding how they actually designed this armor that caught my eye.
Oh! What detail is that?
The document mentions the extensive use of advanced Python simulation tools, specifically tools used to build predictive digital models for high-frequency electromagnetic noise interference and transient dynamic coupling.
Basically, they program a digital twin of the car to simulate the electrical chaos before they ever build the physical circuit board.
Yes. They rely on these digital models to precisely calculate the probability of noise interference and to mathematically set those microscopic software timeout thresholds.
Okay.
But this raises a fascinating and somewhat unsettling question.
I am always here for an unsettling question.
As the automotive industry shifts to even higher voltages, moving from 400 volts to 800 volts, and soon 1,000-volt architectures, and these silicon carbide chips switch at even more staggering speeds, the physical world of copper wiring and metal solder is being pushed to its literal quantum limits.
The electromagnetic machine gun is just getting bigger and firing faster.
Exactly that. So if automotive engineers must now rely on deeply complex Python simulations and AI-driven digital twins to predict these electromagnetic probabilities simply because the physics are too fast, too intertwined, and too complex for human observation, are we reaching an era where human engineers no longer truly comprehend how to fix a physical car?
Wow, let me wrap my head around that. You're asking if the physical reality of the car has become so complex that we can only solve it with software that we barely understand ourselves.
Are we moving past the limits of human mechanical intuition? We may no longer know how to physically bend the metal to make it safe. We merely know how to program an AI twin to calculate the design of the armor for us.
That is incredibly heavy. We started this deep dive by comparing a car breakdown to a clean break on an X-ray. But it turns out the health of your car's network isn't visible on a traditional X-ray at all.
No, it's not.
It relies on microscopic trapdoors, robotically measured crimps and algorithms, watching algorithms, all originally modeled by a digital simulation. Next time you're cruising down the highway merging ahead of a semi-truck, just remember the invisible, furious war being fought and won thousands of times a second under your feet just to keep you rolling straight. Something to think about.